Hello everyone, welcome to the second episode in the series where we're building a 3D model viewer. In the first episode, we were able to create a window and put a nice sky blue color on it. In this episode, we're going to be creating our first triangle. Now, if you know anything about graphics development, you know that creating the first triangle is one of the hardest hurdles in this industry. So knowing that, I'm going to try to explain as much as I can in this video about how all this stuff works, so you're not too confused and we can get over the hardest part together. That being said, I am going to try to keep this concise and digestible at the same time, so this isn't just like a super long, ultra in-depth video. With that being said, let's go ahead and get into it. So I think before we actually just start writing code, I think we need to understand how this pipeline actually works. So I have a really terrible sad excuse of a diagram here, but essentially what we need to do is we need to create a bunch of vertex data. And so our program will create some sort of list of floating point numbers. And then what we have to do is we have to load those numbers into a GPU buffer. And then what we have to do is essentially tell the GPU what all of these numbers mean. So in this case, what we would do is we would take a list of floating point values. And so in this case, what we would tell the GPU is that this block of data is a bunch of floating point values where each pair of 2 is a position. And then when we're done with all of that, we can pass it on to the shader pipeline in the GPU. And so this is a diagram from learnopengl.com, which shows the whole GPU pipeline for rendering. Now don't worry, we don't have to build all these from scratch. A lot of this is actually done for us. But basically it will take in our vertex data, and then the vertex shader will handle the actual positioning of these vertices, and then the fragment shader, which is the second shader that we're going to write, is going to handle the color and appearance of the final output of all of these triangles that are being drawn. So that was a quick overview, but I think that's enough to actually go ahead and get started. So the first thing that we have to do is we have to create our chunk of data that we want to draw. So what I'm going to do is inside of our init function here, I'm going to create a block of floating point values that is going to represent our x, y, and z coordinates of a triangle. So I will create our vertices like this, which is going to be an array, and we're going to need 3 points for our triangle. Now these points are going to be a little bit awkward to write because the coordinate system for OpenGL and other graphics APIs is a little bit weird coming from our own perspective here, because the center of the screen is the position 0, 0, and then the top right is 1, 1, and then the bottom left is -1, -1, which is a little unintuitive for at least me personally, but it's made like this specifically because it makes it a lot easier for 3D applications. So let's go ahead and actually write in these coordinates. So I'm going to do 0.0f for the x value, and then I'm going to do 0.5f for the y value, and then I'm going to do 0.0f for the z value here. And I'm going to put a comment here that this is the x, this is the y, and this is the z. And this is our top coordinate, like this. And let's just make our other entries here. Now I'm going to make this go clockwise, so I'm going to make this one 5, and then the y value is going to be -0.5, and then for the third coordinate it's going to be the bottom left one, so it's going to be -0.5 and then -0.5. Okay, and so now what we need to do is we need to actually put this data into a vertex buffer. Now Sokol has a data type called an SG binding, which we're going to be using here, so I'm going to call this my binding. And so now we can go down here and we can say state.binding.vertex buffers. And if we look at what vertex buffers is, it's basically 8 buffers of data. So we want to use the first buffer, so we will go to the 0th index. Then we'll use a function called sgMakeBuffer like this. This takes in a buffer descriptor, so I'm going to do sgBuffer descriptor here. And what we need is we just need to basically just pass in that data. And what this will do is it will take that data and it will upload it to a GPU buffer. So we'll do data equals, and we need to essentially wrap this in something called an SG range, which is a nice little convenience macro that turns our stack allocated data into a piece of data that has a known size. And because I don't like magic, let's go ahead and look at what this macro does. It's really nothing crazy. All it does is it creates a new SG-range object, which this struct basically has the actual data and a size associated with it. So this is essentially like a slice type if you're used to something like Zig or Go. So it's basically just a chunk of data with a known size associated with it. Be careful with this because this doesn't really work with heap allocated stuff. So because this is on the stack, we can make use of this, which is very, very convenient. Okay, and that's all that we need to actually get our data onto the GPU. But now that the data is on the GPU, we have to create shaders to actually interpret that data and render it onto the screen. So as I mentioned earlier, we have to write at least 2 shaders for our program to work. We need our vertex shader and our fragment shader. But how are we going to write these? What language does the GPU speak? Now, unfortunately, the GPU does not speak plain C code, so we have to write in a shader language. Now, also unfortunately, every graphics API basically has its own bespoke shader language. This is a big problem in the graphics industry, where you have GLSL, HLSL, SPIRV, and a bunch of other things, and we even have shader languages that compile into other shader languages. And so this is really, really not fun if you want a cross-platform application, and luckily Sokol does address this. So there is a tool here that I'm going to be using for this, which is called sokol-shdc, and basically what this does is it allows us to write GLSL and have it compile into a type-checked C header file that cross-compiles it to a bunch of different shader languages that are necessary for different platforms. So this is really, really awesome because it doesn't abstract away the actual writing of shaders. As you can see here, you are still writing GLSL code. You just don't have to write the same shader a bunch of times. So let's go ahead and install this sokol-shdc tool, and luckily the creator of Sokol provides pre-built binaries for a bunch of different operating systems, so go ahead and clone this repository called Sokol tools bin in the description, and then we will have access to those binaries. I'm just going to go to Linux here, and I'm going to copy this over to our project, so back to model viewer, and I'll just stick it in the root because it's very convenient that way. And now what we can do is we can actually write our GLSL shader. So I'm going to create a new directory, and I'm going to call this directory my assets here. And inside of assets, I'm going to create another directory. I'm going to call this our shaders. And then inside of this directory, I will create a new file, and I'm going to call this our triangle.glsl. Now inside of this file, we can create our vertex shader and our fragment shader. Now in order to do that, we have a couple different tags that denote the start and the end of those 2 different shaders. So we have @vs, which basically says this is the beginning of the vertex shader, and I'm just going to call this vertex shader, I guess. Then we can say end here to end that vertex shader, and then we can do fs for the fragment shader, and I'll call this my fragment shader like this, and then do an end right there. And then finally at the bottom, we tell it that this is a complete pipeline, a complete shader program, by doing @program and then putting the name of this, which is going to be triangle, and then the names of all of our shaders, so vertex shader and fragment shader, like that. So now let's go ahead and actually write our shaders. So the first thing we have to do is we have to take in the data that we are receiving from that buffer, right? So the vertex shader works on each individual vertex. And so because of that, we're going to be taking in one set of X, Y, and Z coordinates at a time. So that means that we're going to be taking in a vector 3, or a 3-dimensional vector, which is going to be our position. And now what we need to do is we essentially need to set a special variable that is used in GLSL to denote the actual position on the screen where this coordinate will end up. Now to do this, we first need to create our main function here, because these shaders have their own main function, their own entry point. And this special variable that I'm talking about is GL_position, which is case sensitive. It's lowercase GL_ P and then position equals, and we're just going to set it equal to the position. We're not going to do any sort of transformations or anything to it. We're essentially just taking in the data and presenting it as is. Okay, and now onto the fragment shader. So the fragment shader's job is to colorize the pixels on the screen, and it essentially works 1 pixel at a time. So that means that the fragment shader needs to output an RGBA value for that pixel. So the out for this shader here is going to be a vec4 for each dimension of RGBA. It's a 4-dimensional vector, and this has to be called frag color. It's another special variable. And again, we have our main entry point like this. And for the color, I'm just going to hard code a color for now to keep things simple. So I'll do frag color equals vec4, and then I'm going to make it red. So I will do 1.0, 0.0, 0.0, 1.0, so that we have 100% red, and then we have no green, no blue, and then we have 100% opacity. And that is a pretty minimal shader setup. Okay, and so now to actually compile this into our header file, we're going to use this command here. And so let me just go ahead and describe what's going on here. So we are running this sokol-shdc command, taking in the input file, which is our triangle.glsl file that we just created, and we are outputting a file called triangle_shader.h. And then for the shader language flag here, which is this slang here, we specify all of the different languages that we actually want to export. So I want at least GLSL, HLSL, and metal, because GLSL is good for OpenGL on Linux, HLSL is good for DirectX on Windows, and then metal is good for metal on macOS. So let's go ahead and run this command. And I made a mistake inside of the shader. I forgot that GL position is actually a vector4. So what we need to do is we need to wrap the position in a vec4 and then do a 0.0 at the end, rerun that command, and then we are all done. Now again, I don't like magic, so let's actually look at what this created. So this is the final output, which is a 300 line C header file. And basically this is the source. So it compiles the source into static blocks of memory that it will then dispatch from a function. So there is a function here that is called triangle shader description, which will query the backend, and depending on the backend, it will grab out the correct source and will do all of the necessary platform specific things to get this shader up and running. Very, very convenient for cross-platform graphics development while still remaining relatively low level. Okay, so after that detour, let's actually use this inside of our code. So in order to do that, we're going to need to create a shader pipeline. So I'm going to go to our static struct state and do sg pipeline like this, and this is going to be our pipeline. Then below where we created our vertex buffer, we need to create this pipeline. So I'll do state.pipeline equals, and then it's going to be sg make pipeline, I believe. This takes in a pipeline description, which I hope you can see a pattern of how this library works, right? Because it makes it a little bit more intuitive to sort of guess your way around how things work. Normally the way things work is whenever you want to create something, you have some sort of sg make on that, and then it takes in a descriptor object. So if you do know that, you can sort of guess some features, which is a really good intuition to develop. So we'll do sg pipeline description here, and this takes in a couple different things. The first thing that we need to pass in is the actual shader here, which the shader can be created from a function called sg make shader like this. And this takes in a shader descriptor as well, which here, instead of actually doing our own shader descriptor, what we'll do is instead we will now include our triangle shader.h file here. Then we will use triangle shader description function here, which is given to us from that shader file. And then once we're done with that, we need to pass in the backend so that our shader knows which backend to use. And so we can use a function called sg query backend like this. And that is how we create our shader. Okay, and now that our shader is created, we now need to specify the layout of our data. So I mentioned earlier with this bad diagram here that we need to essentially tell the GPU how to actually interpret this data, because as far as it's concerned, we just passed it a blob of junk and it doesn't know what to do with that data. We need to tell it that it needs to split it up at these intervals, and it needs to interpret this as a vector 3 or a vector 2 or whatever. So to do that, we can add a new field to our sg pipeline descriptor here called our layout, And inside of layout, we need to specify the different attributes and their sizes of our data. Now our data is very, very simple. It's just position coordinates, so we only have one attribute. I'm going to specify our attributes field like this. And then inside of here, we're going to populate this sparse array with some values that are automatically generated inside of our shader header file here. If we actually go to our header file here, you'll see that there is a very, very nice comment section here, which actually gives you a description of the shader, and it will tell you the attributes in this shader, which there's only one, which is our triangle position. So we need to essentially take this value here and go to our layout and paste that value in. And we need to specify the format of it. So the format is in SG, I think it's vertex, what is it? Vertex format, and it's float 3 for 3 floats, which is our vector 3. Okay, and so that is the entire setup part, and now we just need to do the drawing, which is much, much easier. So to do this, we have to go after we begin this render pass, and we need to apply our pipeline. So we've just spent all this time creating the pipeline, now we actually get to use it. So we can do SG apply pipeline like this, and we can pass in our state.pipeline. And then after we apply our pipeline, we need to bind the data that we want to use with this pipeline, because this pipeline is data agnostic. We can use this shader pipeline and this layout on whatever data we want. It doesn't have to make any sense. In this case, we do want to use it on this specific data here. So what we can do now is we can do SG apply bindings, and here we can pass in our state.binding like this. And then finally we can do SG draw, and this takes in a couple values. So the base element is the index of the first element. Then we want to do the number of elements. Now it's important to not confuse this with the length of the array, because our array has 9 elements because there are 9 floating point values in it. This is the number of items that we are actually drawing, right? And so we are drawing 3 vertices, so we want this to be 3. And this is the number of instances, because there is such thing as instance rendering, where you draw multiple copies of the same data. We don't want to do that. We just want to draw 1, so I'll pass in 1 here, and that is that all done there. So let's go ahead and see if we were able to get this first try. So I'll run make, and it looks like I have an error here. It's probably because, yeah, I'm not including Sokol graphics before the triangle shader. That's because of my formatter. It actually stuck it up at the top, which I don't like, so I'm just going to throw it down here so it hopefully behaves, and then run make. And it looks like it did work perfectly fine. So now we can do make run, and we now have a bunch of red, which is not what I was expecting. I did make a mistake when writing this shader, so I originally had this at 0, which is not correct. It should be 1.0, and essentially the reason that it was displaying all red is because whenever we are calculating clip space, what this will do is it will use position.xyz, and it will divide this by the 4th dimension, which is w, which this is undefined because you can't divide by 0, so it's essentially just filling the whole screen with the frag color, basically. So in order to prevent that, we should put this at 1.0, which will actually give you the correct result. So if you do make run, you will see that we now have our triangle. Now I think I can make this triangle look a little bit better, so why don't we actually add color to all of this? So what I will do is inside of main.c, let's actually add in the color values. So I'm going to add in 3 dimensions for each color. So this first one is going to be red, so it's going to be 1.0, 0.0, 0.0. The next one is going to be green, so 0.0, 1.0, and then 0.0. And then the third one is going to be blue, so 0.0, 0.0, 1.0, like this. And now what we have to do is go into our shader here, and then we have to say that we are also taking in a vector 3 of our color. And what we need to do is, now that we're taking in the color, we need to actually pass that color to our fragment shader. So we now actually have an output from our vertex shader. So we're going to do out vec3. I'm just going to call this like out color, you know, sure, why not? And so now inside of main, we need to assign out color to our color. So we'll do out color equals color. And then inside of our fragment shader, we need to take in this out color. So we'll do in vec3 out color, which that's probably a bad name because that's kind of confusing. I'm not good at naming things, unfortunately. And then we will do frag color equals our out color, comma 1.0, because I want it to be full opacity for all of it. Then we have to recompile our shader, so I will run this command here, and I'll actually put this inside of our make file so we don't have to keep on rerunning this long command. I will create a new entry in our make file called shader, and then here I will paste in that command that we keep on running. So now we can just do make shader like this, and it's a lot simpler to do. And now if we go into main.c, we have to edit our pipeline a little bit, so we have to add a new entry here, which is attribute, and this is going to be our triangle color dot format is going to be equal to the SG vertex format float3 like this, and that is now our new pipeline setup. So we can now do make, and we can now run our program, and as you can see, we have a nice colorful triangle like this. Now I'm going to change the background color to match my theme so that it looks a little bit more cohesive. So I'm going to put these floating point values in here to make this look a little bit nicer for my own liking. And look at that, we now have our triangle with my background, so it's all nice and seamless. And I'll just add in some comments here so that it looks a little bit nicer so you can actually see what's going on in this code. And if you're wondering why we didn't destroy any of the bindings or pipelines or anything like that, it's because Sokol handles that for us automatically. We can explicitly destroy them if we do not want them to live for the duration of the program, but Sokol does actually handle freeing everything. And if you want to actually, confirm that for sure, you can go to the code itself and check it out. So if you look at this here, it uses this sgalloc buffer, which this function essentially just allocates onto the Sokol graphics pool, which is just a big pool that it allocates up to a point and then it frees everything at the very end. Very, very convenient for this type of stuff, because in this case, I do want this to live for the entire duration of the program. Now, I'd be lying if I said that this was a simple episode. So I know that this would be quite a lot, especially if you don't have any experience with graphics programming. So I am 100% open to answering any questions that you have, and also answering them on Discord if you want to join my Discord, which is in the description. But just to give a very, very brief recap of everything, because this was a pretty packed episode, essentially what we did here was we got data from the CPU onto the GPU. And the way we did that was we created an array of data and stored that in our memory. And then what we did is we took that data, we uploaded it to the GPU via a vertex buffer. Then we created a pipeline where we created the vertex shader, which decides where the individual vertices go. And then we created a fragment shader, which decides the colors of the pixels on the screen. And then finally, we decided the layout of the data that we actually passed in. So we described to the GPU how it actually interprets this big blob of data. And then after that, we take that pipeline and we take the actual binding and we bind the pipeline and then the bindings of the data, and then we draw everything and finish our render pass. So it is quite a lot of stuff, but now this is done, this is honestly the hardest part of graphics programming. So once you get this, which I do recommend messing around with this, maybe trying to get 2 triangles on the screen, trying to get a quad or something like that. Once you have all this down, you're pretty much ready to go. So with that being said, hopefully you enjoyed, hopefully you learned something new. Again, if you have any questions, make sure to leave them down below or join my Discord and ask more extensive questions there. And if you like this video, make sure to like and subscribe, and also let me know in the comments if you like this type of content and you want me to keep making more. And if you really like this video, consider supporting me on Patreon so I can continue making videos like this. Thank you very much for watching. Have a good day. See ya.